In this section, we're going to take a look at the law of cosines.
The Pythagorean theorem states that given any right triangle where the hypotenuse is opposite the 90-degree angle, we know that the sum of the squares of the two shorter sides that are designated by A and B, we know that the sum of those squares of those two short sides is equal to the square of the remaining side. Right? This is the Pythagorean theorem. And as useful as this has been, it is somewhat limited. Because if you don't have a 90-degree angle here, then this doesn't apply anymore. Well, the law of cosines is going to allow us to do something similar, but without the requirement for a 90-degree angle. So here, let's talk about the law of cosines. All right. So the law of cosines states the following. Let's say we're beginning with a triangle. This doesn't need to be a right triangle, and here I'm going to draw it so that it's not, or at least I'm going to try to draw so that it's not here. Here's an angle which we're going to call A. Here's an angle B, and here's an angle C. Notice this does not need to be a 90-degree angle. These angles are, well, just whatever angles here. So here, if this is the case, then it turns out that it's no longer true that C squared. So here the side opposite is C. Here the side opposite of this is A. And the side opposite of this is B, the way we usually label things. Across from the angle A is a side A. Across from the angle C is side C. And across from the angle B is side B. It's no longer the case that A squared plus B squared is equal to C squared. However, there's still a similar relationship between the side lengths, and that is that C squared is going to equal to A squared plus B squared. And you say, well, that's the same thing we had up here. Well, almost. But now we have this something else, this extra term, and that's going to be minus 2AB cosine of the angle C. This is called the law of sines, and this is going to be true for any triangle. Note, this need not be right. Need not be a right triangle. Okay, so let's go ahead and prove this. The proof of this is, well, let's start off with this illustration here. I'm going to start off with that same triangle, but instead of just having a triangle, I'm going to go ahead and put this on a coordinate system. So let's go and draw out the XY coordinate system. Right, so here's our y-axis, here's our x-axis. And here we can draw the triangle anywhere we like on here, but to make things a little bit nice on ourselves, we're going to take one of the corner points and put it at the origin. Because if something's at the origin, its coordinates are 0, 0, and things are just slightly nicer there. All right, so here are my 3 corner points of my triangle. And again, I'm going to label them A, B, and C, just like I did up here. All right, well then that means the side opposite of this must be A, the side opposite of this must be B, and the side opposite of this must be C. So I know that that's 0, 0 because that's where I put it. This triangle could have been anywhere, so I put it there. Well, notice that this point is also on the x-axis, which means its y-coordinate must be 0. You say, well, what about its x-coordinate? Well, we started at 0, and we went A steps to the right, so that must make it A, 0. All right? From 0 to here, that's how far it is. So that's the x-coordinate. The y-coordinate is 0 since you're still on the x-axis. Okay. Now, this point right here, we're just going to call that x, y. This point right here is x, y because we don't know what it is. It could be anything. But we're going to try to narrow that down a little bit. Consider the fact that this point, you get to this point by starting from 0, 0, going to the right x amount, and then going up y amount. That's where this would come from. If you went right by 3 and up by 5, this would be 3, 5. So this coordinate tells you how far left you go, or left or right, and this one tells you how far up or down you go. Okay, well, notice that this is a right triangle, the one in here. So that means that I can take this angle, C, and I can say things about it. I can say that, well, the side opposite divided by the hypotenuse, well, that's the sine. So I can say the sine of C is equal to the side opposite over the hypotenuse, y over b. Likewise, I can say the cosine of the angle C, well, that's the side adjacent over the hypotenuse. So it's going to be x over b. And here, if I just multiply b to the other side, this will tell me what my x and my y are. This tells me that y is equal to b times the sine of the angle C, and this tells me that x is equal to b times the cosine of the angle C. So here, that's what this point is. So let's go ahead and write that down. That's equal to b cosine of C, comma, b sine of C. Okay? So now what I want to do is I want to say, well, I know things about this angle. Well, that's the side opposite of this angle. So let's see if we can't figure out things about this side length. All right, we know things about the angle. We've just described things involving this angle C. Let's see if we can't tie that in with the side opposite of that. After all, the law of sines allowed us to say, hey, the angle and the side opposite of each other have a relationship. Let's follow through with that. So here, let's see what the length of C is. Well, the length of C is equal to the distance between A and B. Oh, but thinking back to college algebra, we have a formula for the distance between A and B. That is the square root of the sum of the squares of the differences of the components of those 2 points. Or in other words, here, take the x value and take that x value and subtract them. X minus A. Take the y value and the y value and subtract those. All right. X2 minus x1. You take y2 minus y1. You square each of those, add them together, and take a square root. Well, yeah, but we just said x is equal to b cosine of C. And we just said y is equal to b sine of C. So we can write that with a little more detail. Instead of saying x minus A, well, x is b cosine of C minus A. And that whole thing is being squared. Plus, y is equal to b sine of C. And now, minus 0, well, that's not going to change anything, so let me not worry about that, right? So that whole thing will be squared. All right. I could write minus 0, but minus 0 won't make a difference, so let me leave that alone. And now I can go ahead and multiply that out. If I square this, well, let's see, let me do that off to the side. B cosine of C minus A squared means multiply it times itself. Like that. So that'll be B squared cosine squared of C. All right, B times B is B squared. Cosine of C times cosine of C is cosine squared of C. That's going to give me minus AB cosine of C. That's going to give me another minus AB cosine of C. And negative A times negative A will be a positive A squared. So this will give me B squared cosine squared of C minus, well, these are both the same, so let me just double them up. Minus 1 minus another one is minus double that. So minus 2 AB cosine of C plus A squared. Like that. So here, that's going to be what I get when I expand this one out. So let me write that. B squared cosine squared of C minus 2AB cosine of C that's that one, plus A squared. When I square this one, well, then I'm just going to get B squared sine squared of C. Here, this is a single term, so I just square everything inside. Here, this is a binomial, the sum or difference of two terms. So here I can't just square each piece. I actually have to multiply it out. Notice now that these two are very similar to each other. So let me rewrite this as the square root of, here let me take b squared cosine squared of c, and then plus b squared sine squared of c, and let me bunch those together since they're like each other. Here I'm going to have my minus 2ab cosine of c, and then I'm going to have my plus a squared at the very end. So here I just bunch these together since they are so similar. And from these two, I notice I can factor out b squared. So that's going to be the square root of b squared. And if I factor out b squared from each of those, I get cosine squared of c plus sine squared of c minus 2ab cosine of c plus a squared. But notice now that cosine squared of c plus sine squared of c, that's equal to 1. The Pythagorean identity tells us that's equal to 1. So this simplifies down to something very, very small now. We now get b squared minus 2ab cosine of c plus a squared. So here that gives me c is equal to the square root of, here let me go ahead and put these in alphabetical order. Let me put the a first. So a squared plus b squared, and then minus 2ab cosine of c. All I did was I moved that one to the front. All right? So c is equal to that stuff right there. So I just rewrote that. C is equal to, I put the a squared in the front, I left the b squared right there, and I left the minus 2ab cosine of c right there. And finally, c is a positive number. I know that because c is the length of the side of a triangle. That can't be negative. So if I square both sides, I don't have to worry about changing my sign. So here I can just write that as c squared is equal to, well, here the square root, that's going to go away. I don't have to worry about pluses or minuses. So here I just get a squared plus b squared minus 2ab times the cosine of c, which is exactly what the law of cosine says I was supposed to get. C squared is equal to a squared plus b squared minus 2ab cosine of c. C squared is equal to a squared plus b squared minus 2ab cosine of c. And that is the end of our proof. All right? So this confirms the law of cosines. Now, incidentally, here I said something about the angle C, and that tells us something about the side length C. Incidentally, you can do other forms of the law of cosines. Here we could just rotate around and say, you know, instead of calling this C, let's call this an A, or let's call this one B. And if you rotate around, you get other versions of the same thing. If you start with A instead of C, you're going to get a squared is equal to b squared plus c squared minus 2bc times the cosine of a. And if you start with b squared, you're going to get a squared plus c squared minus 2ac cosine of b. Okay. Notice here that one that you start with is always the angle here. B with B, C with C. Here, this is always going to be, well, the other two. So if here I start with A, I use B and C. And same thing over here, B and C. If I start with B, I use A and C. And same thing right here, A and C. And if I start with C, well, here I'd use A and B. And same thing here, I use A and B. And then, of course, these always match. So the law of cosines is the more generic version of the Pythagorean theorem. Notice it looks almost the same, but now instead of having to have a right triangle, now it doesn't matter what kind of triangle we have. This will work out for us. So let's take some examples and see how the law of cosines works in application. All right, so let's just do the same kind of problems we were doing before. Let's solve a triangle. We'll see some other applications here in a moment. So example, solve the triangle. Oh, if I knew how to spell, there we go, solve the triangle, where we're given the information. Let's see, A, B, C, A, B, C. All right, we're given that the angle C is equal to 28.3. We're given that the side length B is equal to 5.5. 4.71 centimeters. And we're given that the side length A is equal to 4.21 centimeters, just like this. Okay. Notice that we cannot use the law of sines here, because the law of sines would require us either to have this pair of angle and side length, or this pair of angle and side length, or this pair of angle and side length. So we can't use the law of sines. Here we can't use that angle to figure out those angles because we only have one. If we had two, we could use those two to figure out the third one because they have to add up to 180. But just one of them is not enough. So here we can't use the law of sines, nor can we figure out any of the remaining angles using this one. But notice here we have what's given to us by one version of the law of cosines. I have a little a, a little b, and the angle C. Hey, look, little a, little b, little a, little b, angle C. So here, using that third version of the law of cosines, I want to say the Pythagorean theorem, the law of cosines allows us to use this information that's given to find the side length C. All right? So here we're going to say C squared is equal to a squared plus b squared minus 2ab cosine of the angle C. All right, that's the law of cosines. And now we're just going to plug in the appropriate numbers. Here we get that C squared is equal to 4.21 squared plus 5.71 squared. I'm taking my A, plugging it in there. My B goes there. Minus 2 times A, which is 4.21, times C, which is 5.71, times the cosine of the angle C, which we're told is 28.3 degrees. Okay. So now we can go ahead and compute that. Let's see what we get. We're going to get 4.21 squared plus 5.71 squared minus all of these multiplied together. So I'm going to have 28.3. I'm going to take the cosine of that. I'm going to multiply it by 5.71. Times 28.3 cosine of that. All right, times 4.21 times 2. And that's going to give me 7.996433703. So here I get C squared is equal to 7.996433703. But of course, I don't want C squared. I'm just looking for C. So now I can take the square root of both sides and see what we get. And so here we get that C is equal to the square root of that number there. We are going to round, but not until the very end. You never round until the last step here. So we take the square root of both sides, and that's going to be equal to 2.8277966616. But of course, notice that all of your levels of accuracy here are only to 2 decimal places. So here we're unjustified in saying it goes out that far. So here we can say, oh, well, let's go ahead and round it to the second decimal place, to the hundredths. Since that number is 5 or more, this will round up to the next decimal place. So 2.83. So right here, the side length C is 2.83 centimeters. Okay. Notice this is slightly more complicated to use in the Pythagorean theorem because of these extra factors here, which give you one extra term. But it's not that much harder to use. You're still using a couple of numbers that you know to figure out the number that's missing. But now, notice that we have, hey, now we can use the law of sines. Because now we have an angle and a side that are opposite of each other. Now, I have mentioned in the past that we try not to use side lengths if we can avoid it. We try to avoid using side lengths that we found if we can avoid it. Here, we would rather use information that was given rather than one that we found. However, unless you use this one, you can't proceed. There's nothing else we can do without this one. So we try not to. If there's ever any other information available, we won't use this one. But we don't have anything else available, so we're going to have to. Okay, so now let's set up the law of sines. In the previous section, we saw that if we take the sine of that angle, 28.3 degrees, divided by the side length opposite of it, 2.83 centimeters, that's going to equal to the sine of, and here I'll just pick one, I'll say sine of A over the side length little a, 4.21. So that means that the sine of A is going to equal to, I could just multiply that up there, that'll give me 4.21 times the sine of 28.3 degrees over 2.83. And let's see what that gives us. That's going to give us 28.3. I'm going to take the sine of that. Now I'm going to multiply that by 4.21. And then I'm going to divide that by 2.83. And that's going to give me about 0.705 or so. So here that sine of A is equal to this big number, 0.705269031. But of course, we don't want the sine of A. We just want A. So let's take the inverse sine. All right, if I take the inverse sine here, that'll make this go away. Gives me just my A. But then I have to take the inverse sine of the other side. So let's see what happens there. We're going to take the inverse sine, and that's going to give us 44.85 128,282. But of course, that's unjustified. Here, all of our angles are rounded to the nearest tenths place, 1 decimal unit. So here, let's go ahead and round that off. So here, that means A is approximately equal to, that's a 5 or bigger, so this will round up to 44.9 degrees. All right, so coming up over here, that would be 44.9 degrees. Now, remember, whenever you take an arc sine, an inverse sine, you may get a second answer. So even though A is this answer, it could also be it could also be 180 minus 44.9, which is, well, let's see, 180 minus 44.9, and that's going to be 135.1 degrees. So careful, we might end up with two triangles here. There's this one or this one. All right, so coming up over here, let's go ahead and write that out. This is going to be, well, let's see. If I add these two together, these two angles, that's going to be 44.9 plus 28.3. That'll give me 73.1. Oh, sorry, 73.2, which is way less than 180. So yeah, that would leave me plenty of room for another angle. Okay, let's add these two together. If I add 135.1 plus 28.3, that'll give me 163.4, which is less than 180. So that would leave me room for another angle. So here, either of these is hypothetically possible. So here, let's go ahead and write that out. Here we could say A is equal to 44.9. Or it could be 135.1. Both of these hypothetically are possible. Okay, so now let's figure out what our third one is. Here, we don't need to go through the law of sines or cosines or anything else. Here, let's just see what's left. If I add these two together, if I take 44.9 and I add that to 28.3, that's going to add up to 73.2. So these two angles already add up to 73.2. And if I subtract that from 180, that would tell me, oh, then this must be the angle 106.8 degrees. But remember, it didn't have to be this one. It could have been this one. So instead of saying 44.9 plus 28.3, we could do 135.1 plus 28.3. 135.1 plus 28.3, that's 163.4. And now if I subtract that from 180, that's going to give me 16.6 degrees. You say, oh, so we have two triangles. Well, maybe. Let's double check this. Remember, one thing that should always happen for any triangle is that the shortest side should always be opposite the shortest angle. The longest side should always be opposite the longest angle, right? So here, okay, that's the shortest side, and that's opposite of the shortest angle. That's the longest side, and that's opposite the longest angle. Okay, that works out. Okay, let's see if this one works. This is the shortest side, and it's opposite of the shortest angle. No, because this angle's shorter. Oh, okay, so if I use this combination of angles, it may satisfy the law of sines, but it still doesn't work geometrically, right? Because here, if I say, okay, my other triangle had A was equal to 153.2, B was equal to 16.6, and C was the 28.3 that I started with in the beginning, that doesn't work out. Because here, the side length A is not the longest, but the angle A is the biggest. Oh, that shouldn't happen. So here, this does not work geometrically. So we can throw that one out. So here it turns out that we don't have two angles. We're just going to have the one. We're just going to have one triangle. And this is our result. So be mindful of that whenever you're using the law of sines, you may or may not get an extra angle. So be mindful to check and make sure that whatever you get makes sense. Okay? And that is our result. Here, let's try another one. Let's start off with an example here where we're not given any angles. Here, let's say we're asked to solve the triangle. That side length A is 4.0 centimeters, B is 5.0 centimeters, and C is 8.0 centimeters. Looks just like that. And now, it would help if I knew how to spell, all right? We're going to go ahead and solve the triangle. Here, we know all the sides. We don't know any of the angles. Okay, well, that's fine. Because the law of cosine says if you give me two sides and an angle, I can figure out that remaining side. But if I know all three sides, well, that means I know all the information except that angle, which means I can solve for that angle too. So here, let's go ahead and do that. I'm going to take c squared is equal to a squared plus b squared minus 2ab times the cosine of the angle c. For this example, I know 4, I know 5, and I know 8 are the side lengths A, B, and C. So give that a try. Pause the video and see if you can go through and find the angle C. Once you find the angle C, see if you can use that information to help you find the remaining angles A and B. Once you're done, go ahead and unpause the video and we'll go through it together. All right, so let's go ahead and pop in our numbers. This is going to be 8 squared. It should be 8.0, but 8.0 is the same as 8. Here, this is true for our level of precision, but for our computation, we can just write 8. So 8 squared is equal to 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of the angle C. We know these numbers. 8 squared is 64. 4 squared is 16, and 5 squared is 25. Negative 2 times 4 is negative 8. Negative 8 times 5 is negative 40. Cosine of the angle C. Here I could add these numbers together. That's 41. So 64 equals 41 minus 40 cosine of the angle C. Do not subtract these. I see people do that all the time. 41 minus 40 gives you 1. No. These are separate. Here, this is not the number 40. It's 40 times the cosine of the angle C. So don't combine those. Here, let's subtract the 41 over to the other side. So minus 41 and minus 41. And that'll give us 23 is equal to negative 40 times the cosine of the angle C. Let me go ahead and divide both sides by a negative 40. And that gives me that the cosine of C, now by itself, since these are gone, is going to give me negative 23 over 40. Oh, well then that must mean that if I take the inverse cosine of this side, I'll just get C. And if I take the inverse cosine of this side, well, let's see what happens. If I take the arc cosine of negative 23 over 40, over 40, let's see here. If I take negative 23 over 40, and I take the inverse cosine, that's going to give me 125.099632. So here this is equal to 125.099632. Unlike the law of sines, when you take an inverse sine, there's different possible angles you could get for a triangle. When you take an inverse cosine, that's not going to happen. All right? In the previous example, we saw, I take the inverse sine, so I might get different angles. Maybe, maybe not. Law of cosines or taking an inverse cosine doesn't do that at all. Here, that's the only thing it could be. Okay, so here, let's go ahead and round that off, because of course everything here is up to 1 decimal of precision. So here we're going to go ahead and round that to 1 decimal of precision, which is 125.1. Okay, so there's our angle C, 125.1 degrees. Okay. We can now use that information to figure out the remaining bits of information. Here, let's see, that's 125.1 degree. Okay. Now here, I could use the law of sines. Yeah, but we try not to use something that we found. You say, well, what other choice do I have? I mean, that's the only angle that I found. We could use the law of cosines again. After all, we have c squared is equal to a squared plus b squared minus 2ab cosine of c, which means using that, I could find the angle c. But there are other versions of the law of cosines. Remember, these are all equivalent. So if I'm missing the angle c, well, then I should use this bottom one. But if I use the top one, I could find the angle a. Or if I use the middle one, I could find the angle b. And that would only be using these 3 side lengths and not an angle, which means it would be more precise. So here, let's go ahead and go through that. Let's go through using the law of cosines again. I'm going to pick one of the other 2 versions. I'm going to pick the one that will give me the angle A. So here I can write this as A squared is equal to B squared plus C squared minus 2BC cosine of the angle A. Okay, so I just plug in the numbers that I know. I know A is 4, so that'll be 4 squared is equal to B is 5 and C is 8. So that's 4 squared is equal to 5 squared plus 8 squared minus 2 times 5 times 8 times the cosine of the angle A. Okay? So once we finish with this one, it'll give us that first angle. All right, so now we can go ahead and simplify some of these numbers. That's 16 is equal to 25 plus 64 minus, that's 10 times 8 is 80, cosine of the angle A. If I add these together, that's going to give me 89. So 16 equals 89 minus 80 times the cosine of the angle A. I can now subtract that 89 over to the other side. And that's gone. That's a positive minus a big number. That'll give me a negative. That'll give me a negative 73 is equal to negative 80 times the cosine of the angle A. And now if I divide both sides by a negative 80, that's going to go away. And that's going to leave me just the cosine of A by itself. Double negative will cancel out, so that's going to give me 73 over 80. And so if the cosine of A is equal to that number, I want the A by itself, so let me take the inverse cosine of the cosine of A. And that's going to equal to the inverse cosine of 73 over 80. So I'm going to take the inverse cosine of the left side, take the inverse cosine of the right side. Here, that's just going to give me the angle A. All right. And now here, the inverse cosine of 73 over 80. That's going to give me 24.146848. just like that. But of course here that's an unrequited level of precision. Here we have everything's out to 1 decimal place. So here let's go ahead and round off the angle A to be approximately 24.1 degrees. Just like that. So here that's 24.1 degrees. And now we have 2 angles. Now we can actually find the third one by just subtracting both of those from 180. All right? Here, these are numbers that we found, but subtracting them from 180 is precise enough because, of course, all angles must add up to 180 anyway. So here, our third computation is the simplest. Here we can simply say, well, A plus B plus C is equal to 180 degrees. But here we're missing B. Oh, so let's go ahead and solve for B by subtracting the A and the C over to the other side. Minus A and minus C. Minus A and minus C. And that gives us that B is equal to 180 minus A minus C, which is 180 minus 24.1 minus 125.1, which is, we take 180 minus 24.1 minus 125.1, we end up with 30.8 degrees. And so that must be our final side. And finally, as a quick little check, the shortest angle is opposite the shortest side. Yeah, that's true. The biggest angle is opposite the longest side. Yeah, that's true. So here, that is the correct result. Right? Note one thing here. Whenever we use the law of sines, we may get multiple angles. Sorry, not the law of sines. Whenever we use an inverse sign, we may get multiple angles. Whenever we use an inverse cosine, that's not going to happen. Here, we didn't even try to check for another angle. This will give you a unique answer between 0 and 180. So here, this doesn't yield you possible alternate results. So just keep that in mind. Inverse sines might give you multiple triangles. But if you use an inverse cosine, there's only one angle that could yield, which means there's only one triangle that could yield. Well, one angle between 0 and 180 anyway. All right, so now let's take a look at a couple of application problems. We're in an airplane or we're up high somewhere. And here's our airplane, because that's what airplanes look like. They look like little bumblebees. And you're looking down at 2 objects. There's one here, and there's one over here. All right. All right, so now we're given some information. We're told that from this flat line, looking straight out from the airplane, to look at this first object, we'd have to look down at an angle of 24 degrees. Okay? And then we're told that to look at this further point, we'd have to look down at, well, we don't have to look down as much, right? It's not close to you, it's further out. So you're only going to look down 17 degrees. Okay, just like that. And you're told that you know the distance from this to this, and it's given by 5,120 feet. Almost a mile. All right. So now the question is, how far apart are these? So the question is, find the distance. Here I'll call this the point A and call this the point B. Find the distance from A to B. Okay. Now, I have an angle, because notice, if this whole angle is 24 degrees and this angle right here is 17 degrees, well, then the difference of those, that 7 degrees difference, must be the angle between here and here. 17 plus another 7 would be the full 24. Okay, so I know this angle, and I know this side length. So if I just knew this side length, I could use the law of cosines. All right? If I knew this side length, I'd be done with my problem. All right, well, let's see if we can figure out this side length. Well, notice that this side length is dependent on this right triangle right here. Okay, so let me separate out a couple of right triangles. Here, instead of having one big complicated looking picture, let me separate this out into two simpler pictures. I have one triangle that looks like this. All right. My angle is 24 degrees right here. And I know nothing about this length or this length or this length. I know nothing about it. All right. I have a second triangle. This one over here that's got a 17 degree. Let me draw it the same way. 17 degree angle. All right, here's a triangle right here. And that's got a 17 degree angle, and I know this hypotenuse is 5,120. Okay? Now these are right triangles because this angle is from the horizontal straight down. So here, this is a right triangle. Same thing over here, this is a right triangle. Oh, okay, well since those are right triangles, look what I can do. That's the opposite, the adjacent, and the hypotenuse. Notice that this elevation and this elevation must be the same. Again, this is a perfectly flat line, and this is the flat line, the ground. So whatever this height is must be the same as this height. So if I can figure out this height, I'll figure out this one. Okay, so I want something about this angle. I want to figure out the side opposite, and I know the hypotenuse. Oh, that's going to be sine. The sine of 17 degrees is equal to the side opposite, which is my height, over my hypotenuse. So that means the height, this elevation here, must be equal to, if I take that 5120 and multiply it over here, it's 5120 times the sine of 17 degrees. All right, so let's go ahead and do that. That's going to be the sine of 17 degrees times 5120. And that's going to give me h is equal to 1496.943128. Okay? So we're not done with our problem. We're not going to round this. We're going to leave that exactly as it is. And here we now know that this is this height right here. We don't round anything until the very last steps. So here this is 1496.943128. Oh, but I can just pull the same trick because I know the side opposite, and if I can figure out this hypotenuse, that'll figure out this side. Okay, so then that's the sine of 24 degrees is equal to the side opposite, which is at 1496.943128 over this hypotenuse, which, I don't know, I'll call it, I already use h for something. Let's just call it, I don't know, w, because why not? All right, that's w. Okay, so that's opposite over w, which means that if I now multiply w to this side, that'll give me w equals sine of 24 degrees. Oh, sorry, w times sine of 24 degrees is 1496.943128. And if I divide both sides by the sine of 24, that'll give me my w. So this will give me sine, let's see, this will give me 1496.943128 times the, divided by the sine of 24 degrees. So let's see what that gives us. I still have that old number on my calculator, the 1496 point something. So now let's just divide that by the sine of 24. And that's going to give me 36. Oh, let's see, what is that? 3680. So that's going to be a 3680.374399. So that gives us the length from here to here. 3680.374399. Okay. Again, I'm not rounding that until the very end. I'm going to keep all of my precision, and at the very, very end, when you get your answer, that's when you round. So now we're almost done. Notice I have a triangle. Now this is not a right triangle. It's got a 7-degree angle, and here these are both definitely not 90. But I have an angle and two of the side lengths, which means using the law of cosines, I can now finish this off. Let me go ahead and draw that last triangle over here. That's going to be this triangle here. I'm going to just draw it on its own. Okay, that's the angle 7 degrees. Here, that's going to be the side length. Let's see, that's 5120. And over here, this is the side length, 3680.374399. We will round at the very, very end. So now we're just about done. Because notice, if I call this the angle A, which I did before, that was my A in my original drawing, and there's my B, and up there's my C. Here's A, B, and C. C is the side length that I want. Okay, so then by the law of cosines, I can now write this as C squared is equal to A squared plus B squared minus 2AB times the cosine of the angle C. Oh, but I know all those numbers, so let me just plug them in. That's going to be C squared is equal to, here's my A squared, 3,680.374399 squared, plus, oh, here's my B. Oh, actually, I have those backwards. That should be my A, and that should be my B. But I'm doing the same thing to both, so it doesn't really matter. All right, that was A squared plus B squared. I accidentally wrote them backwards, but since it's addition, it doesn't matter. A squared plus B squared minus 2 times A times B times the cosine of the angle C, which we see is 7 degrees. And now we're just about done. That's now a calculator problem. Let's type all that in and see what we get. All right, so let's see here. We've got 3680.374399. I'm going to square that, plus 5120, square that, and then minus, and here my calculator needs parentheses because that's a big expression. So that's going to be the cosine of 7 degrees times 3680.374399 times 5,120 times 2 equals to that big old number. So here we get C squared is equal to 2,353,435.307. Right? But then we need to take the square root of both sides. So here that gives us that C is equal to the square root of that very large number. Which, if I take the square root of that, will give me 1,534.091036. Okay, but of course, and that is our answer now. That is our value of the distance between A and B, right? That is the value of C here. So that is our answer. But here we wanted this rounded to. We noticed that our only distance here was rounded to the nearest 10 feet, 5,120. Okay, it might have been 5,121 or 5,119. It's rounded to the nearest 10 feet. So here, our answer is going to be rounded to the nearest 10 feet. So here we get that C is approximately 1,530 feet. And there we go. So our distance from A to C is going to be 1,530 feet. There we go.